Now we've seen how important first and second derivatives of a function is to understanding the shape of the curve that the function draws out. Let's have a look at actually sketching curves using this information. In the textbook there's a list of steps to go through to do this, but we'll go through some examples to see how to do this intuitively. Let's try and sketch the curve x to the 4 minus 4x cubed plus 10. So the key steps for this, really the important steps for this, is to find the first and second derivatives, to find where they go to 0, and to find where they change sign. And from using this we can piece together what the function looks like. So the key steps are, we want to find the maxima and minima, which means that we need a sign table for the first derivative. And we also want the concavity regions. So therefore we want a sign table for the second derivative. Let's go about constructing these and see if we can sketch the function using this information. First we find the first derivative and then read off immediately where the first derivative is 0. And from this we'll construct a sign table. So the way to think about this is the x-axis as a number line with x equals 0 and x equals 3 marked off on it, where we know that the derivative of f goes to 0. And then in each of the regions we just write in what the sign is. So left of x equals 0, if x is negative, then it's clear that because this x squared is always positive, x minus 3 is negative when x is negative. To the left of x equals 0, the sign of f prime is negative. In fact, to the left of x equals 3, it's also negative. And to the right of x equals 3, when x is larger than 3, this term becomes positive, and the first derivative is then greater than 0. So it's a good idea just to sketch what that tells us about the function. It's decreasing in this region, decreasing in this region, increasing in this region, and so we can see that x equals 3 is a minimum. Now let's look at the concavity. For this we need the second derivative, 12x into x minus 2. And so we can see then that the second derivative goes to 0 at x equals 0 and x equals 2. So these might be points of inflection. But to confirm that, we need to do a sign table. Now, the sign of this function when x is less than 0 is a negative number times a negative number, so that's positive. Then if x is less than 0 but greater than 2, we have the function is negative, and for x larger than 2, it's positive. So if we just sketch what this means in terms of concave up or concave down, we have a region which is concave up, concave down, concave up. So where the concavity changes sign, we have a point of inflection. So these are both points of inflection. What about that asymptotic behavior? That is, what happens as x approaches plus infinity or minus infinity? Well, polynomials always tend to plus or minus infinity as x gets larger and larger in either direction, and because of the sign of the leading term of this polynomial, which is x to the 4, that's positive, which means that the function itself goes off to plus infinity at plus and minus infinity. So the function goes off to infinity in both directions. So from this then we can see the general shape is going to look something like this. To the left of x equals 0, the function is decreasing, but the derivative goes to 0 x equals 0. It then continues to decrease past this point of inflection, but with a concavity which is now changing sign. The concavity changes then at x equals 2 to concave up, and there is a minimum at x equals 3 before the function goes off to infinity. So x equals 3 and x equals 2 is a point of inflection. So we have a PI, point of inflection, and a minimum. So using the derivative, the first and second derivatives and sign tables of, allows us to do a rough sketch of what the function is going to look like. And in order to make a more accurate sketch, we just need to add a few points in. So typical examples of where to do this are the origin and are the critical numbers and the points of inflection. So these help anchor our graph, if you like. We know that at x equals 0, the function takes the value 10. At x equals 2, it takes the value minus 6. And at x equals 3, it takes the value minus 17. So adding this in then, we can sketch a graph of the function. Let's label in some important points. So at the origin, the function goes through 10. At the point 2 and 3, if we just mark those off, the function goes through the point -6 and -17. We have a curve which looks something like this. And we can compare that to a plot from a computer. Let's try a different type of function now. Let's have a look at the function e to the x over 1 plus e to the x. And we need to pick this function apart a little bit in a bit more detail than we did last time. So first we need to have some information from f. And for that we'll have a look at it's a point on the curve. So let's have some information from f. What do we know about the function? Well, it's always positive, and we can also see that it's also less than 1 for all x in R. So in fact, we can see that it has asymptotes. If we take the limit, then as x tends to infinity, e to the x becomes arbitrarily large. This 1 in here becomes less and less relevant, and we have e to the x over e to the x. So that asymptotic behavior as x tends to infinity is just 1. As x tends to minus infinity, e to the x is tending to 0, and so we end up with just 0 over 1, which is just 0. And note also that at the origin, the function goes through the point 1/2. That's plenty of information about the function just from analysing its behaviour in the asymptotic regimes. Now what about the function's derivatives? Let's have a look at the first derivative. So if we differentiate the function, what we find is we get e to the x. So when we differentiate the numerator and the denominator, we find these two terms. And as a way to understand what's going on here, let's write this as f of x, first term is just the function itself, minus the function squared. And we can see then that since f of x is positive but always less than 1, we can see then that the derivative is positive everywhere, because if f is less than 1, then f squared is smaller than f. So that implies the function has a derivative which is positive everywhere, and so the function is increasing everywhere. So it's always getting larger and larger. Now for the second derivative, well, we can use this from our formula above, as it's the first derivative minus 2 times the function times the first derivative again. So this is equal to f prime of x times 1 minus 2. And the reason I've done it like this is because we know this first term is greater than 0, and this second term equals 0 when f of x equals half, which we know corresponds to x equals 0. So the concavity changes sign at x equals 0, which means this is a point of inflection. So it's concave up to the left of x equals 0 and concave down to the right of x equals 0. So putting all this together then, we're going to get a graph as follows. Now let's draw in the horizontal asymptote at y equals 1. So we know that the function is trapped between these two curves. It's increasing from 0 all the way up to 1 from the left. As we approach infinity to the right, we're heading off in this direction, and coming from the left, we're also coming from y equals 0. Function's always increasing with a point of inflection where the concavity changes sign at the origin. It's increasing when concave up to this point, and then it's increasing but concave down from this point. And again, we can compare to the real function that's plotted on a computer. Let's look at a final example which has a complicated feature at the origin. Let's look at the function e to the 1 over x. What does this look like? Well, again, let's look for information from the function first to see what's going on, and then we'll have a look at the derivatives and see what they tell us about the function. So first off, we can note that it's positive everywhere, but we can also see that there's problems at the origin when x tends to 0. And to analyse those, let's use limits. So let's look at the limit as x tends to 0, but from the right-hand side. Now, as x is approaching 0 from the right, it's always positive, so the 1 over x term is tending off to infinity. So e to that power is just infinity. So the function then, as we approach from the right, is plus infinity. Now, as we approach from the left, 1 over x is tending to minus infinity, and e to the minus infinity is 0. So we have then something around the origin which looks like this. function tending to 0 and tending to infinity on the right hand side. So discontinuity of the function. Now let's find the asymptotic behavior. So as x is tending to infinity, 1 over x is tending to 0, and so e to the 1 over x is tending to 1. So these both then tend to 1. Now let's look at the derivatives. The first derivative is minus 1 over x squared times e to the 1 over x, which is less than 0 for all x. The function isn't defined at x equals 0, of course, so this means that the function is decreasing everywhere. Now for the second derivative, this factors into 2x plus 1 over x to the 4 times e to the 1 over x. And then clearly there's a sign change at x equals a half. So if we just do a quick sign table, it's concave down in this region and concave up to the right of x equals minus a half. So concavity changes at x equals minus a half, so it's a point of inflection. Putting this together then, we can draw a sketch of this function. So we've got y equals 1 is the asymptote from the left and the right, coming in from here to the left and then heading off to 1 as x tends to plus infinity. As we approach the origin from the right hand side, so as we come in this way, what's happening is that the function is heading off to plus infinity. So it's heading off like that. There's no other points of inflection or maxima and minima in that region, so we can just join those two regions together. And as we approach the origin for the left, we know that we're coming in this direction and that it's concave up in that region with a point of inflection somewhere here at minus a half. So we have the function coming in like so, but it's not defined at the origin. So we indicate that with a circle. And the function from the left, joining that all up then, means that to the left of the origin, the function looks something like this. And again, we can compare to a computer-generated sketch of the function.